Okay. Yes.
Did you upload the PowerPoint for chapter 12?
Yes, I just uploaded that, and the chapter 12 assignments are now available for you to begin looking at. That said, 11's due tonight, focus on that. So, and in keeping with that, we're going to talk about the chapter 11 assignments today. Some common questions that I can ask about them, and any questions that you guys have. Miscellaneous reminders. I'm sorry if a bunch of people are having tests this week, but we will have a test next week. But to try to make that as easy as possible, it will be an out-of-class web assignment test, the web assignment test. You'll have 5 hours to complete. It's only designed to take 1 hour, but you'll have 5 because everything takes longer over the internet. Leading up to that, we have this week, we're going to spend on chapter 12. The chapter 12 assignment will be due the 23rd. This will also be the day that the test opens, but you won't have to have it done until, let's say, Friday. That way everyone can take advantage of the lab period that they don't have lab for. Cool.
So we don't have lab next week?
We don't have lab next week. So if you haven't heard yet, announcement, no lab next week, because since I'm making the test out of class, I don't want you to have to worry about scrambling to a lab and then scrambling to take the test. So to make sure everyone has that amount of time free up. So no lab next week. There will be a lab the week after, and there is a lab this week, but not next week. Cool. So, 12 this week, sorry, chapter 11 stuff is due today. We'll learn about chapter 12 this week. Chapter 12 will be due this night, and that's when the test will begin to be able to be taken. And that'll last. You'll have the option to do it at any point that week. And we'll spend that week talking, reviewing, going over things. I don't want to. I lost my train of thought.
Will we review that? We have class Thursday, right?
Yes.
Will we also have like time to review that Thursday?
Yes, so class this week might be a little bit weird because we have the test out of class, and that means that all of class time will be dedicated to just reviewing for people who haven't taken it yet. Which means if you take it, say, on Wednesday, the rest of the week will mostly just be reviewing people who haven't taken it yet. And so, strictly speaking, I don't require you to be in this room anyway, but specifically those days, once you take it, the rest of the week is review and studying. You might not specifically feel the need to be here those days, which I understand and won't ask you to be here that day because we're not covering anything new. So there's less point in it. I will go ahead and put up the next couple homeworks and notes so that you can begin looking at them once you finish the test. And you can come ask about those, but no obligation. Yes?
The chapter 13 homework won't be due the next Tuesday, right? Like it'll be the week after.
Right.
Like since we won't learn chapter 13 yet, it won't be due that Tuesday.
Correct. And
Yeah.
officially speaking, our next chapter will be 15.
Right.
I absolutely understand what you're saying. This is test week, meaning it's not learning week. So this is learning week, chapter 15 onwards. I'll make the materials available to you at this point because I'd like you to look at them, but I won't have an assignment due this day if we take a test and then haven't finished it yet. Any other questions? Okay, well, time for different questions. Chapter 11 homework then. Is there anything specific? What was the specific first thing you had?
So, like 5 and 6
like, I know that in number 6, it tells you specifically if there is trapped air. But for 5, after numerous attempts, I figured out that it also wants air, but like, why does it want air, the R value of air?
I've had a lot of people report problems with 5. And the issue with 5 is it doesn't say that there's an air layer in there, which would explain why the answers that I have been finding with everyone are smaller than what the computer wants. So I can see the answers that people have been submitting, I can see what the computer wants for everyone's specific cases, and the computer is always guessing higher than I would have thought.
Because, like, so I got the lower answer and it was like, oh, you're 10% off of the, yeah, right? So then I looked at the next problem and that one added the air. So then I said, okay, like I added an inside and an outside layer of air, and then when I did that, like the R values for that, it counted it right. But like, we never did that, so I don't know.
You're right, and I don't know why it's doing that, frankly. I would like it to say that, but it doesn't. So I should be able to change the wording of the question. That said, if you've already submitted an answer to, if you've submitted an answer for Chapter 11, homework number 5, and it was wrong, and it's wrong because you didn't factor in the air value that the question doesn't tell you to factor in, please tell me, and I'll make sure you get your points. Because I don't know why it does that. And I didn't realize that's what it was doing until you told me just now. For some reason, I just thought it had a value set too high. But if that's what it's doing, then it probably needs to say it. And this is me being frustrated about the side. Yes.
To solve this problem, we can just add the layers together.
Correct.
The R, right? The R value layers, if you just add together, that gives you like the total R value.
Because it's the sum, yeah.
Yes, if we take a quick look at the formulas, for a single layer, we add E equals Ka, TH minus TC over L. This was a single layer. The multiple layers is A, TH minus TC over sum of all the L's and over all of their K's. But the American Construction Company has compressed that into R's. So, this one constant refers to the conductivity of any thickness of any multiple layers of materials. As long as you know what those materials are and what their thicknesses are, you can look at and this is in the notes posted online, so this chart is free to access. So whatever materials it says, you just find them on the table, and then you add them together, sum of the R's to create the R for that particular wall. And if, for instance, you had 2 inches of brick instead of 4 inches of brick, just cut it in half. So, for looking at 5, ignoring the air for a second because the problem doesn't say that there's air. We have lap shingles. So we go to the table, we look up lapped wood shingles. We've also got 50 inches thick of sheathing, which should there is an entry for, just sheathing, half an inch thick. And then some amount of cellulose fiber. Everyone will have a slightly different number here. The thing you're meant to do is convert the number for 1 inch of cellulose fiber into whatever it needs to be for X times that. And then half an inch of drywall. There is an entry for half an inch of drywall. If I was grading this based on purely this question, that would be it. You just add those 4 things together. 1, 2, 3, 4. Yes. The Phys1510 is a dumb robot computer. So for some reason it has in its head that there needs to be 2 air layers. If you added those 4 things together and that was your answer and the computer yelled at you, please tell me and I will fix it. I am not going to require you to go back in and change it just to make the computer happy. Yes?
So for the air layer, is that the stagnant layer of air that we add in?
Yes.
Yeah.
Stagnant air. As long as it's not windy and as long as the air isn't, as long as the heat isn't rising up or down, if it's horizontal air, then the stagnant air layer 0.17 would be what one uses. And apparently thickness doesn't matter for air layers, which is probably why double pane glass only has a very thin air layer in it. As long as it's there, it does something. And 6 is a very similar type of question. Here we've got existing 2 glass panes. We have measurements for all the things that make up that glass. The temperature difference from inside the house compared to outside the house. And area of the window. Determine the R of the window and then find the thermal power through the whole window versus just a single piece of glass. Yes.
Okay. Formulas.
Formulas.
I understand that the bottom one with the R, right, that's for the construction one, because those have specific R values and like, but when it's not like a construction problem, you would use the second one, right? Because you would be given L's and K's, or, yeah.
Yes.
But I don't understand what the first formula is for, and the difference between those and the other one.
Between this and this?
Yeah.
So the first one assumes just one thickness of one material. This would be like a solid chunk of glass and nothing else. Because we just have 1K, it's one surface area, and it's one thickness. This version compresses the K and the L together, and we look at every single K and L for every material present in whatever layers we're looking at. So sigma L over K, you're adding up every single length divided by every single K. Then you've got 3 layers. You'll have 1 layer of glass, glass thickness divided by glass K, and then plus air thickness divided by air K, so on and so forth for however many layers there are. So, I don't know why I was checking my pockets. Single material multiple materials This is also multiple materials, but U.S. construction.
To solve 6, would you use the second equation for the first question?
For 6, you should be able to use either. There's a bit of a trick either way, though. If we use the second equation, the constants on that table for American feet and Fahrenheit values are going to give us power in British thermal units per hour. So if you use this, you would then need to convert your powers into joules per second. If If we used this version, our answers would come out in watts, joules per second, but we would need to solve for and then add together all the L's over K's.
And K is thermal conductivity, right?
K is the coefficient of thermal conductivity. The P is the rate of thermal conduction itself. It's the actual rate. K is a constant that tells you how conductive a single material type is.
And that chart is on the PowerPoint?
Yes, it is. The one we were just looking at is the R chart on the multiple layers US construction version. So this is the Fahrenheit feet and BTUs version. But there's also the other chart somewhere. Let me take these animations out. This is the metric version for joules per second, meters in Celsius. And this one does have glass and air. So we can use this if we do the sum of all the L's over K's. That way, if we did this version, our answer would come out in joules per second. So there's one extra step in your version.
What's your unit for L again?
L is length, thickness, so meters, or feet for this version. Well, I guess there's no L in that version.
The sixth one was talking about like glass panes, so you would just take the one from glass, since it's not on like the construction one.
Yes, so a thermopane window consists of two glass panes. Those two panes are made of glass, so that tells us what K to use. They're each this thick, so we'll have two layers of glass this thick, and so that's going to be one L over K and a different L over K. And then between them is 1 centimeter of sealed stagnant air. So that's the thickness and the material of the third layer.
Do you have to convert the centimeters into meters, or does that matter?
It would be best to, because either this needs to be meters so that this can be meters squared. If you leave this as centimeters, it would be okay if this was in centimeters cubed and if K was designed for centimeters. So I do think the most straightforward thing would be to convert all your L's into meters first.
And then for the single pane, do you switch to the first one to just one layer, one material, or do you still use the second equation?
Second one is just a single pane of this thick glass. So for that one, we can just use the normal version. It's a solid layer of a known thickness of a known material. Yes.
We're doing 3.
Yes.
Number 3. Have been asked about 3. Which one is 3? Ah, okay. So 3. Okay. So for 3, I really only care about D. That's the entire reason it's up here. This is just meant to be a combination phase change thermal energy transfer question. I don't necessarily care about any of this work being shown to me. Sorry I did not elaborate on that further up until now. The reason this question is here is to do the conversion and the transfer math to get to this final temperature. You don't need to graph things, you don't need to write things out and turn it in by hand. As a general rule, I believe as with your last semester as well, when the question says do this on paper and show your instructor, you don't need to. It's a virtual assignment. That is just preamble. So don't worry about making a graph. That said, let's look at what we do need to worry about. We have 3 materials being combined, some amount of aluminum at this temperature, some amount of ethyl alcohol at this temperature, and some amount of ice at this temperature. And these three things are going to sit together until they reach thermal equilibrium and are all at the same final temperature, as most things in thermal contact tend to do. And the ultimate goal is simply to find that final equilibrium temperature. Now, when asked about 3, sorry, because I kind of jumped the gun, what was the original question that you specifically had?
I've like done it 3 times and I can't get the answer.
Okay, so let's set it up. There is some good insight in pieces of this little preamble, namely this letter A right here. Identify the 5 thermal energy phenomena that would have to go on here. So, looking at the materials that we are mixing, we have solid aluminum that is warmer than freezing, ethyl alcohol that is warmer than freezing, and ice that is below freezing. Before we ever put pen to paper, just your instincts, what do you think is going to happen to the ice in this situation? The ice will melt, and so do you think the final temperature will be above freezing or below freezing? Okay, so there's 5 things that are going to happen here to get us to that final equilibrium temperature. 1, ice has to warm up. It's going to take some amount of thermal energy gained by the ice to get it up to melting point before the second thing can happen, ice melts.
So this is like a phase change diagram in words.
Yes. Second thing, now that it's water, the water will warm up to the final temperature. And all the while, the H2O is gaining thermal energy. Where is it gaining it from? It's gaining heat, but where's that heat coming from?
Aluminum and alcohol.
Correct. The 2 things warmer than it are giving it that thermal energy. So aluminum cools and ethyl alcohol cools. So these are the 5 things that are going to take place. The 5 thermal reactions.
And you assume that at the end, everything is the same temperature.
Yes. If you leave any 2 things touching long enough, they'll eventually get there. We're keeping all 5 steps, but all 3 of these particular objects locked in together, touching for an extreme length of time, and no thermal energy is leaving the system or entering the system. It should eventually end up at the same final combined temperature, and that's what we're looking for. So, these things are going to have to occur, and we can separate these things into 2 different categories. The first 3 listed here all have to do with the H2O gaining thermal energy. So these can all be sorted under our Q gain. All of these are a net increase for the water, right, for the H2O. Meanwhile, the aluminum and the ethyl are cooling down, so these can be described as Q lost. These 2 are losing thermal energy, and since it's a closed system, that energy has to go into these. And this tells us what side of the equal sign each of these particular phases is going to go when we write out. Why is this marker on me?
Okay, I have a question.
Yes.
So for chemistry, we do like the net opposite with the negative sign.
Ah.
So why? Like, why does it work both ways?
Well, Because multiplying both sides by a -1 and dividing both sides by a -1 ultimately accomplish the same thing. If we wanted to send this negative over to the other side, we could simply multiply both sides by -1. That'll cancel it here and send it over there.
So like it doesn't super matter where you put it, it just matters that you put it.
Yes. I like it on the lost side because that'll cancel with the negative inside of the lost.
Yeah.
That's just me.
Well, I did too, and then I was doing that, and then Kevin, and then he would write it opposite. I'm like, am I doing something wrong? But then now I know that it's the same thing.
It is the same thing. So I write it like this. If you have a different preferred method, either putting the negative on the gain side or by keeping the absolute value brackets, that is okay. I am not the end-all be-all of how to do science math. If you have a method that works for you, please use it and don't let me distract you from it. This is just how I write it because I've had many different teachers drill different versions into my head and they've all coalesced into this. Ink. Yay. Okay. So, on our Q lost side, we have two things that are losing thermal energy. That's aluminum and the ethyl alcohol. So, we are going, and they are only cooling down. There's no phase change. So we're going to have an MC delta T for the aluminum. And an MC delta T for the ethyl alcohol. Meanwhile, as that side loses thermal energy, the H2O is going to gain it. We have an MC delta T for the ice warming up. Then the phase change itself, which is going to be the one part of this that is not an MC delta T. That's mass of ice times latent heat of fusion. Thank you. And then, now that it's melted, one more MC delta T for the water. And I've been writing delta T up here, but ultimately the thing we're going to be solving for is T final, which is going to be a part of most of these delta T's. So, of the 4 delta T's up here, 3 of them will have that unknown T final in them. This is the only one that wouldn't, because the ice is going from a known starting temperature to its melting point, which is also known.
0?
Correct. So, I believe, yes, everyone's ice begins at -10, and it's going to warm up to 0. So, delta T for the ice is going to end up being +10 for everybody. So, this will ultimately just compress all the way down to a single number. But every other delta T here, the water will go from 0 to temperature final. The ethyl is going to cool down from 30 to temperature final, and then the aluminum will cool from 20 to temperature final. So that's 3 TFs you're going to have to algebra your way into being together on one side.
And once you get on that one, I think you just solve for quantity.
Sorry, one more time.
I said, once you get that all of one, once you get T final by itself, then you just solve.
Yes. Ultimate goal is just TF. And as long as you are plugging in all these Celsius temperatures, the answer should pop out in Celsius.
Oh, for 2, what is the mass of the iron? Oh my God, per kilogram of iron. I didn't see.
It's okay. Yes, if you plug in 1 kilogram of of iron, then it'll tell you how much water per 1 kilogram of iron.
How much water per 1?
plug in 1 kilogram of iron, then you'll get the amount of water needed for that 1 kilogram of iron. You're okay. There's a lot of words and numbers floating around. Yes?
For number 7, I got a really big number and I feel like it's not supposed to be. And I don't
7.
know what, yeah, I was like, I think it's supposed to be really big, but I don't know what I did wrong. I don't know if I'm multiplying in the wrong places or if I'm adding the wrong things.
Did you convert grams to kilograms?
I did.
Okay, good. One more second. Just, I'm just going to need to take a look at it.
Cause like it's kind of a mess. But, so I multiplied the grams of ice times the heat diffusion.
Okay.
And then, I did 2 for some reason times the 186. And then added the ice and water parts to that.
Mhm.
And then added the copper, specific heat, and then plus its grams, and then divided by the specific heat of lead minus the temperature.
Mhm.
Is it like that?
Yes, although I might need to. I think I'd
Oh,
like
that's
to.
a 12 for the temperature equilibrium. And I multiplied that by this one.
Hang on.
That's the first one.
I think I'd like to set it up on the board.
That's fine. I'm ready to do that, because like I said, I don't know exactly what I did wrong, but I said that it was like, that, like in the thousands, I was like, that's not right.
Let's set up 7 together because I don't have that in front of me and I need to check what happened there. So, let's just read through 7. We have ice floating in water, and all of that is in a copper cup. All those masses are known, which is convenient. They all begin at a temperature of 0 Celsius. A extra thing is dropped into the cup, a piece of hot lead, which is the last thing anyone wants in their beverage. One of the last things. And after that lead is dropped in, the final temperature of the entire concoction is 12 Celsius. That is the mass of the lead that was dropped in. It then lists these specific heats and latent heats and all that is needed to complete every reaction going on here. So, I like to set this up the same way. Q lost minus Q gain, sorry, Q lost equals Q gain, excuse me. So the one thing losing thermal energy in this entire thing is going to be the lead. It starts hot and will end colder than it was. So we will have MC delta T, I don't know. For the lead, which I'm going to write as PB because chemistry. It wasn't until I had to teach a little bit of chemistry that I finally knew what the Latin names for all the elements were. Now finally one of them makes sense. Okay, so lead losing thermal energy. Everything else is going to gain thermal energy. That includes the copper cup. It's going to warm up from 0 to 12. You know what? I'm going to write in the temperatures up here. That'd be a little more helpful. So we will have lead cool to 12 from your starting temperature. My numbers are 98. You can put your own starting temperature in here. The copper cup is going to warm up. So we have mass of copper times specific heat of copper times my temperatures are 12 to 0. Those will be the same for everybody. Copper warms up, the water warms up. ice. It's already at 0 Celsius, so what's the first thing the ice is going to do? Not your question.
Like melt.
It'll melt. The ice is already, there's ice in this water, the whole thing's at 0 Celsius. If you add thermal energy to it, the ice is going to start melting.
Well, that makes sense because that, if you didn't say that it would melt, then you would have two of the same equation. Like for that.
You absolutely are going to, because
Right.
the mass of water is effectively decreasing as the ice shrinks. So there's two ways you could do it. You could treat the water, the amount that started as water, keep it separate, and then keep adding in the ice as you go. Alternatively, you're still going to need to do mass ice times latent heat of fusion. And you could simply just make this mass the combined mass of the water and ice if you wanted to compress that. But in an attempt to try to keep everything as distinct as possible. So we have one thing losing thermal energy, that's the lead. Everything else, copper warms up, water warms up, ice melts, and then melted water warms up, is all on the gaining energy side. And the final thing to end up solving for is massive lead.
When you divide because you wouldn't leave the negative out, so you divide the negative over, can you distribute that and make that, the parentheses like -12 plus 98, or does it matter?
That is what I would do to avoid sending a negative over, because 12 minus 98 is a negative number. It doesn't, as long as all your starting temperature is already a big positive number, which they should be, this will be negative and it should just cancel with this negative. And so ultimately you're just going to divide over positive specific heat of lead and positive temperature difference. Does that help?
Yes.
Okay. I didn't see the difference at a first glance from whatever you had. Excuse me. I know this assignment is short in case, since that there's only a few questions, like there's fewer than normal questions on it, but that's due to the fact that we all have a lot more individual parts to them. How do you guys feel about this assignment?
It took you longer than the last one.
Well, I mean, things get more rigorous as the semester goes on, better than it starting too hard. I don't know. That said, I fully believe you guys are able to do this, and as always, if the computer is yelling at you, something doesn't make sense, you think you're doing it right, but WebAssign just isn't having it, email me questions and email me your work, because I will retroactively add partial credit if the computer just screws you over. But that should help everyone get through all the 11 assignments. The quizzes are the same, just guided, short practice problems. And just a quick glance, window. I was getting some questions about 4, so just very briefly. This question does have thermal power in it, but the main formula you're going to want to employ is actually Q equals MC delta T. You want to figure out how much thermal energy you need to warm up the aluminum in the water, then use the power given to figure out how long it would take to produce that thermal energy. So even though there's thermal power present, this is not a conductivity question. Cool.
Wait, can you say that one more time? how you use the power right now?
So, in this particular question, we have a burner that is producing this much thermal power. So every single hour it gives off this many BTUs, every single second it gives off so many joules. All those joules are being funneled directly into an aluminum pot with water in it. So all that energy every single second is going into the metal and the water combined. You want the water and subsequently the pot it's in to heat up to the boiling point of water. So you need to find how much energy it will take to get that amount of aluminum from 20 degrees to 100 degrees and the amount of energy it will take to get this water from 20 degrees to 100 degrees. Because all that energy has to come from the burner. So once you know that total energy requirement, you can use the burner's power rating to figure out how long it takes to make it. You will need to convert BTUs per hour to joules per second. And for the sake of fairness, mouse. Put this on the corner over there so it can stay there. 1 BTU per hour is approximately 0.29 joules per second. Oops. And as a further reminder, joules per second is watts. So that should set everyone up for all of 11. I'd like to at least glance at 12 before we break for today. These notes are on the website, so I recommend taking a look at them once you're wrapped up with your 11 stuff. And I just want to take a second to glance at it to promise you you've seen all these before. Chapter 12 is where we're finally going to begin describing the laws of thermodynamics directly. You've dealt with all of these before, so you're going to take them one law at a time and start doing the math thereof. And yes, there are technically 4 of them, because we really liked having our 3 laws of thermodynamics, probably because we also have 3 laws of motion from Newton, who just likes symmetry. Humanity really likes the rule of 3. But some physicists felt that we really needed this qualifying statement before people started studying the rest of the laws. And rather than make it the 4th law of thermodynamics, they made it the 0th. Because humans do be like that. And it really is a very inconsequential law. It's basically just the communicative property of temperatures. If, say, the blue marker is in thermal equilibrium with the green marker, and the green marker is in thermal equilibrium with the orange marker, what must be true for both the blue and orange combined? Thermal equilibrium. If A equals B and B equals C, then A must also equal C. That's all it says. Not entirely sure why that needed to be added as a qualifying statement, but it has been, so someone must have needed it at some point. The other 3 laws you have definitely interacted with, probably because this one was part of your formulas last semester and still is. First law of thermodynamics, also known as conservation of energy. Created or destroyed is a total constant, it just changes forms and locations. The second law, a little more contentious, total entropy level of the entire universe either stays constant or rises, it never drops. Has anyone in this room not studied entropy to any capacity? Okay. I don't want to spend too much time on it because it doesn't show up in most of the physics related at this particular class level, but we will just conceptually address it, one or two formulas involving it. The third law pairs weird, interestingly, with the second law, because entropy is related to the thermal energy level of a single object. If you look at the entropy level of one thing instead of the universe as a whole, you can reduce the entropy level of one thing by just removing its thermal energy. The less thermal energy something has, the less chaotic its particles move, the less entropy it technically has. And if you reduce something's thermal energy level all the way to the lowest possible point, absolute zero, that object would theoretically have no entropy in that moment. The entropy of a system, that can be a single object, approaches a constant value. That value is zero as its temperature approaches absolute zero. That said, this doesn't break the second law, because in order to make that one thing less entropic, you have to remove its thermal energy and put it somewhere else, thereby raising that other place's entropy level by the same amount, if not more. So, the universe as a whole is increasingly becoming more chaotic. You can make single parts of the universe less chaotic at the expense of making something else more chaotic. And we'll just spend the rest of the week looking at various formulas and principles related to these particular concepts. These are pretty big things in the physics world. It's right up there with Newton's laws and subsequently other electromagnetic laws further down the line, which is why they get their own chapter. So, that's the end of the lecture. That clock is fast, and I'm finally learning that. If you have any questions or grievances about the homework or the quiz at all, please let me know as soon as possible so that I can get them fixed. There is a lab today. The first lab graded, and I'll give them back during that period. Thank you all. See you soon. Have a wonderful day. And it was a nice one today, but I heard it was